Okay, hello again. We're moving on to Chapter 2, Psychology's Scientific Method. So in this chapter, we will take a look at the scientific method, how it applies to psychological research. We'll also go into statistics, not quite as much as you would in a full stats course, but just so we understand how statistics helps us to analyze and interpret data. We'll always be cognizant of ethics. Right? We'll think critically about our findings, and as always, we'll try to understand how all of this applies to health and wellness. So during normal times, this chapter is admittedly a little dry. Not a lot of normal people find statistics and research super interesting. Apologies to Mr. Thomless and Converse, but you're not normal. But right now, in these very confusing and trying times, this chapter takes on a whole new level of importance. The things we will discuss in this chapter will help you to filter through the barrage of information that we're subjected to every day, through news media, social media, in talking with friends and family. This chapter is all about giving you the tools you need to understand and think about the issues that our country and our world are facing right now. As we discussed in the last chapter, psychology is a very broad field, and throughout its history, psychologists have studied all kinds of phenomena. Most studies focused on everyday things like social interactions, childhood development, and aging. Some focus on abnormal behaviors like psychological disorders. They could focus on brain chemistry of schizophrenia, aversive conditioning, and OCD. And you'll occasionally run into some very odd studies into things like telepathy and acupuncture. What is important is not what you study, but how you study it. Taking the last two things as an example, scientific studies have shown that there is no such thing as telepathy, telekinesis, mediums, or fortune tellers. None of these phenomena stand up to scientific scrutiny. Other practices that we once thought were kind of esoteric and not based in science turn out to actually have some merit. Acupuncture, for example, has led to very effective treatments like NPS that physical therapists now use to treat a variety of issues. So how do we do this? Well, the first thing is to always keep in mind that science is a method. Now, that may sound like an empty phrase, but think about what it really means. You may see on the news or on the internet a headline like, "Science proves such and such," or "Science can do this or it can't do that." What any of those articles or people are really saying is that the application of the scientific method has shown X. So scientists propose theories to explain phenomena. As we mentioned in the last chapter, those theories represent the best evidence we have so far. Some theories are very well supported and hard to refute. Again, things like gravity, evolution, atomic theory, quantum theory. Others are good, but they're continually evolving. A lot of theories in nutrition are like this. They may be true, but don't always give a complete explanation, and therefore are being constantly revised and updated. And again, this reinforces the idea that science is a process. It's not always perfect, and scientists do not always get it right the first time. In fact, they rarely do. We're constantly rejecting, supporting, and refining theories. Now, we do that in a methodical fashion. We observe, hypothesize, test, draw conclusions, and then evaluate. So I was on lunch duty one year, and I started to notice some interesting behaviors in the student body. I was curious, and I began really watching the self-seating patterns of students in different grades. I hypothesized that younger students tended to segregate themselves by gender, while older students did not. In other words, freshman boys sat only with freshman boys, girls with girls, but by the time they were seniors, the lunch tables were much more mixed and heterogeneous. So remember, a hypothesis is a testable prediction, and it's derived from some prior theory. Now, in order to test that hypothesis, I would have to do further study. In this case, it would be a naturalistic observation. I would have to know which students were freshmen, sophomores, etc., and then track their seating patterns over time. Then I would look at my results and analyze the data. From there, I would draw some conclusions. But as you may already be thinking, there could be some problems with my study. For one thing, the reliability of the study. So we'll talk about that more in a little bit. The next thing I would do is evaluate the theory, or more specifically, I'd ask other people to evaluate my theory. I'd publish my findings and my claims and hope that other scientists would attempt to reproduce the study. If they do, they may come to the same conclusion, thereby supporting my claim. Or they might not, meaning that the theory or findings need to be updated in some way. So the example I just gave would be considered descriptive research. It's based on observation of an organism in its natural environment. Descriptive research can be something like surveys, interviews, case studies. As you may recall, William Lunt did a lot of case studies, talking to individuals and people about their experiences. Descriptive research is very useful. It shows us what is happening. Yes, younger students self-segregate by gender in the lunchroom. It does not explain why they do that. And we have to be very careful about making any assumptions. Correlational research can show us the strength of a relationship. We see this type of research a lot in psychology. And again, it's very useful, but we must be careful. When we say a relationship, we mean a relationship between two variables. For example, what is the relationship between height and shoe size? We would probably discover a pretty strong correlation between these two things. In other words, as height increases, so does shoe size. It might not be a perfect relationship or have a correlation coefficient of 1, but it would be very close and therefore very strong. In this case, we would also say it has a positive relationship. So in psychology, positive and negative never mean good or bad. They're used in a mathematical sense. So here, a positive correlation is one in which both variables increase. As height increases, shoe size increases. Or in the example above, as this lecture goes on and on and on, students yawn more. We could change the variables a little and look at the relationship between length of lecture and student attentiveness, in which case we would probably discover a negative relationship. As one goes up, the other goes down. The reason we have to be careful with correlational research is because it only shows a relationship. It doesn't tell you why it's happening. I could claim that as students yawn, I tend to talk longer. In other words, correlation does not equal causation. Here's a good example of this problem. Take a minute to pause this video and write down 3 reasons why you think parental harshness relates to child rebellion. Here are a few possible explanations. Maybe harsh parents drive their kids to rebellion. Maybe rebellious kids drive their parents to harshness. Maybe there's a third factor or variable at work. Stress, for example, could be affecting both parents and kids. Maybe the behavior has a genetic cause. There may be more explanations or some combination of all of these. The point is that just showing the correlation does not explain why it's occurring. In order to prove causation, we have to do an experiment. Now, there are several factors that separate an experiment from other types of research. First and foremost is the separation of subjects into groups via random assignment. So let's say I want to know if my new medication is effective in treating migraine headaches. This would actually be a quasi-experiment. If you recall that term from our last chapter, it's quasi because I would get a sample of participants who already suffer from migraine headaches. Now, in a true experiment, the subjects do not already have the condition that I'm studying. In this case, they would, because it would be unethical for me to purposefully give them a migraine. Quasi-experiments are used a lot because we can't give someone autism, for example. We can't give somebody cancer to see if our new medication works. True experiments can be done and are done a lot when we study things like sleep deprivation. So in this case, I have a sample of people who all suffer from migraine headaches on a fairly regular basis. I randomly separate them into 2 groups. One, the experimental group, gets my new medication, which they are told to take as soon as they experience a migraine attack. The other group, or the control group, gets what we call a placebo, a pill that has no measurable effect. It's essentially just starch or sugar and in such small quantities they would have no biological impact on the subject. Then I asked the subjects in each group to record the severity and duration of their migraine headaches. If my hypothesis is correct, the experimental group will experience shorter, less severe headaches. In this experiment, the independent variable is the medication, and the dependent variable is the severity of the migraine. The value of an experiment is that it's the only way to prove causation. By separating my participants into random experimental and control groups, I have proven that it was, in fact, the medication that caused the change. So the example I just gave is very medical and pretty straightforward, and it's never quite that easy in psychology. We always have to consider how valid the results of the experiment are. Now we have two types of validity, external and internal. External validity shows us the results of the experiment would hold true outside of the laboratory or testing setting. Now, this is probably not a problem in the example we just gave, but it's a significant issue for many studies. Internal validity asks if the results of the experiment were, in fact, due to the manipulation of the independent variable. So in our example case, it was actually the medication that caused a decrease in the severity of the migraines. Now, at first you might think, yes, of course it was, because we didn't do anything else to the experimental group. But we must always be cautious of bias. So what if, in our example, I told each person what I thought the medication was going to do, and then asked them to report their experience to me? What I have done is created all kinds of potential problems. Experimenter bias might occur because I want my hypothesis to be proven true. So when a subject who I know is in the experimental group tells me their migraine was a little bit better, I interpret a little bit as a measurable amount, and I might quantify that as an improvement of 2 on a scale of 1 to 10. But then a subject in the control group tells me that their migraine wasn't as bad but didn't change very much. And since I know that they got the placebo, I interpret that statement as a 1 on a scale of 1 to 10. But what's the difference between a little better and not as bad? We can eliminate this type of bias by first making sure that the subject is the one rating their change on a scale and not the experimenter. And then ensure that the person interviewing the subject does not know which group the subject was in. Now, obviously, somebody has to know which group the subjects are in, but not until after the data has been collected. That way, the person conducting the experiment and interviewing the subjects does not see only what they expect to see. Now, next, we have to take into account demand characteristics and participant bias. The subjects know that they are in a study to measure the effects of medication on migraines. Right away, that knowledge is going to change their behavior and skew the results. Now, this can happen in a variety of ways. It could be what we call the good participant role, where the subject feels like they should be on your side and they want to help you out, so they say, "Oh yes, I feel much better," when really they only feel like a little bit better, or not at all. On the other hand, we could get someone who comes in thinking, well, nothing can help them, and so they say, "Nope, didn't really help me at all," when in fact the migraine was much shorter and less severe. This is the negative participant role. We can never fully eliminate the effects of demand characteristics or participant bias, but we can account for them in our data and by assuring random assignment to different groups and a healthy sample size. Another related issue is a placebo effect. Of course, if we tell the subjects that they are taking a fake pill, then they probably won't report any change. But sometimes we see that the placebo or the control group who doesn't know that the pill is inactive will still report a significant improvement and sometimes even report side effects. This is called the placebo effect, and it happens so frequently that we have to account for it. So we do what's called a double-blind study. The participant does not know if they're receiving the real medication or the placebo. The person collecting the reports or doing the interviews does not know which group the subjects are in. Again, someone behind the scenes knows who's who, but they do not interact in any way with the subjects. They only look at the data from the reports. And then we say, that the experimental group improved X amount when compared to placebo. Now, note, we always say when compared to placebo because we know that the placebo group also reported a change when compared to people not taking any medication or when compared to their own experience prior to the study. Listen to some drug commercials on TV, and you will hear this phrase a lot. We're going to end this lesson with the following question. Do we judge attractive strangers as more honest? So that's my research question. You're going to come up with ways in which we would study this question. Describe how we would conduct the following types of research, from observations all the way through to a full experiment that shows causation.